In the previous video, we've seen that we can recursively estimate our belief over the state with the Bayes filter. However, in order for this to be practical, we will need to make some assumptions or simplifications. In this lecture, we'll see a practical example of the Bayes filter called the Kalman filter that makes some specific assumptions. Recall that we require two probabilistic models to perform recursive estimation, the process model and the measurement model. The Kalman filter assumes that these models are linear, that the initial belief follows a Gaussian distribution, and that the noise models are additive and zero mean Gaussian. Here are those three assumptions written in math. Here we'll assume that the initial state is parametrized by some mean vector mu with a covariance matrix sigma. The process and measurement model noise variables are both Gaussians with zero mean and diagonal covariance matrices Q and R respectively. In this setting, we can show that the Bayes filter equations can be reduced to simple linear algebra operations. Here we show the equations and refer the interested student to the supplementary material for a full derivation. Let's look at the first row for prediction. The Kalman filter propagates the mean through the noiseless linear process model and updates the associated covariance matrix. In the case of updating, things are a little bit more complicated. We don't go through the details here, but the key idea is that we need some way to decide how to balance our current belief about our state with what the new measurement is telling us. This is calculated as the Kalman gain K, shown as the last equation on the bottom right. In the first equation, we updated the mean as the weighted sum of our prior mean and the difference between the measurement and what our measurement model predicted that the measurement should have been based on the mean state multiplied by K. This difference is referred to as the innovation. Similarly with the covariance, the K matrix tells us how much we should reduce our uncertainty based on this new measurement that we just got. However, if we refer again to our kinematics model, is it linear? Take a second and think about it. In fact, it's not linear because these sinusoidal functions are nonlinear. What about our camera model? Is it linear? It's not either because we always have to divide by z in the camera model. In the case that we have nonlinear models but still assume that the noise is normally distributed, we can apply the extended Kalman filter, or EKF. The EKF uses a first-order Taylor series expansion around the mean estimate at each time step for each of the process model and the measurement model. In a first-order Taylor series expansion, we need to find the matrices of partial derivatives called the Jacobians. In this case, we actually need 4 Jacobian matrices which capture all of the dependencies between the states and the noise parameters. Once we have these matrices, we can apply the same equations as we did for the Kalman filter. We can still feed our mean through the nonlinear process and measurement models, but everywhere that we needed the matrices of the linear model for the Kalman filter, we can replace them with the associated Jacobian matrices. Let's see how this would work with an example. Here's our Duckiebot sitting on the road in Duckietown. For now, we're only going to concern ourselves with the Duckiebot's angle relative to the lane and its orthogonal distance to the center of the lane. We know that we initially placed the robot in the middle of the lane pointing straight down the road. We can initialize our state with low covariance. Now suppose that we command the robot to drive straight for some period of time. The robot might not drive exactly straight because of noise in the system. We can feed these control values into our EKF propagation equation to get our prior belief bell bar. Shown in the bottom left is a graph where the distance from the center of the lane on the vertical axis and the angle relative to the lane on the horizontal axis. The level curve of a Gaussian is always an ellipse. Here we show the 1 sigma level curve to represent our uncertainty in the d phi plane. Notice that in the case of prediction, our uncertainty about our state only ever increases. Next, we get a camera image, and in that image we detect a yellow line. This yellow line tells us something about where we are in the road. We project that line to the ground plane using our homography matrix. This line corresponds to a measurement that we can use to update our estimate and get our posterior belief. In this case, our uncertainty shrinks around the true Duckiebot location. One consideration with any state estimation technique is how robust it will be to outliers, or measurements that don't follow the statistical model. In this video, we can see that there are a lot of correct line detections, but a lot of bad ones too. In the case of the EKF, outliers can be devastating if the measurements are trusted, in other words, have low covariances associated with them. In this case, we will get a large innovation and a large common gain, causing our estimate to become far from the ground truth, but also overconfident. To make matters worse, the next time we linearize, we'll be linearizing around the wrong point, so it's likely that our estimate will continue to diverge. The common filter and extended common filter are very effective as long as the modeling assumptions are not violated. This is probably the most commonly used filtering technique in practice.